injectives instead of projectives. So there's very little change. So today I want to go from Tor, and these guys were the derived functors to tensor product, to ext. And these guys are going to be the derived functors to hom. So these are left derived functors of this tensor product functor, and these are going to be the right derived functors of hom functor. And well, this guy was adjoint to hom, so I would expect some adjointness between ext and Tor. So recall that when your functor f is right exact, like this state in the tensor product, and you have an object, say A, an object in your category, in the abelian category where this functor f is defined, then you take a projective resolution of that guy, and this requires the existence of projective resolutions in that category A. So you need to check this, that this exists. This wasn't for free on an arbitrary category. You need to check that this exists. We checked, for example, that this does exist if the category A is the category of modules for a given ring. But we haven't checked that this, well, we can't check that this exists for an arbitrary abelian category because that's not true. So you take a projective resolution, then you apply your functor, and this is a chain complex in that category, and then you take the homology of that complex. And this you declare to be these left derived functors of f applied to A. And we check that this does not depend on the projective resolution. Okay, so the same board, we're going to do this for, let's say that now that G is left exact, so for example, G is hom. G is hom from X to something. So that's a left exact functor. Then you're going to compute the right guys, the right derived functors by doing the following. You take an injective resolution in your category. And again, you need to check that this exists. So there's same requirement. You need to check that this exists. Might not. We haven't even checked this in this category. So today we want to check that this does exist in the category of R modules for an arbitrary ring. But okay, so we take an injective resolution, you apply your functor, and this is again a chain complex in the same category, in this category A, and you take the homology of that. You declare this to be the right derived functors of the functor G applied to A. So now, the fact that this does not depend on the injective resolution is proven in exactly the same way, and actually we can use the proof. Once we know that we have such resolutions, then we can just use this proof for projectives, just by turning around arrows. Something that holds for a category A is the same if you turn around arrows, to a theorem that holds in the category A of. So given the fact that resolutions exist, the fact that this thing does not depend on the resolution is proven in exactly the same way. So this is a good definition as long as we have enough injectives, as long as we have enough resolutions. So the fact that every object has an injective resolution follows from the fact that there are enough injective, namely for any object there's an injection into an injective object, and that's equivalent to the same statement we've proven for projectives. Every object has a projective resolution that we constructed, assuming that from every object admits a surjection from a projective object. So we did that construction, turn around arrows, and you're going to get the same construction for injectives. So, but we need to check that the category of R module has enough injectives. This we haven't done, so this is different. All right, so how do we do that? I've given already one description of injectivity. Remember, what was the definition of an object being injective? So whenever you have an injection in your category and a map like this, so this is an injector, then this guy exists. So this exists, making this diagram commute. And recall that if the category is the category of R modules, then this injection here, I, can be taken to be is enough to check for I being the inclusion of an ideal inside of the ring. For I, an ideal inside R. And again, so if this is a category of left modules, then this should be a left ideal. And if I'm looking at the category of right R modules, then this should be a right ideal. But either way, we've checked that. I mean, of course, if this holds for any injection, then it's going to hold for those. But we checked that if this holds for these ideals, then it holds in general for arbitrary modules. So that was one of the theorems proved that this is an equivalence, and this was called Bayer's criterion. So apply that criterion to the case where R is Z. So we look at the category of Z modules of abelian groups. Or more generally, this is something I've already used. I think I've given an example of an injective, of a non-divisible module. But more generally, if R is a PID, a principal ideal domain, the same is going to happen. And let's analyze what this theorem says. Okay, so what this condition of a module being an injective, if and only if you can lift these kinds of injections from an ideal. So okay, so let's pick an injective object in the category of R modules. So let's suppose that M, I don't want to use I as an injective this time because I want to reserve I to be an ideal of the ring. So let's suppose that M is an R module that is injective. So let's pick an element inside of this guy. And let's pick an element in the ring. So we can cook up an R module map from R to M that just sends 1 to m. And this extends uniquely to an R module map, because R is the R module generated by 1. Okay. The fact that R is a domain says that multiplication by R, as long as this guy is non-zero, then R is not a zero divisor. So multiplication by R is injective from R to R. And the fact that M is injective now implies that this guy exists. So this means that there exists some M prime in M such that R times M prime is equal to M. And this was the definition of M is divisible. Conversely, any ideal in R, and now I'm going to use the fact that R is a PID. So conversely, for any injection I inside of R, now this ideal is the ideal generated by an element R. So this means that this ideal is the image of multiplication by R. Means that if I look at this, I land on I, which is inside of R. Now let's suppose that M is divisible. And you can always cook up this R module map, sends 1 to 1. Now if M is 1 to M, if M is divisible, then this guy exists, just by definition of being divisible. So this means that we can just lift any map from R to M. We look at what is the image of 1, that gives us an element in M. We look at what this multiplication by R is. This gives us the situation where we have an injection of an ideal inside of the ring, and we can just lift it. So we can lift every injection of this form where A is an ideal inside of V, and these are all ideals because my ring was a principal ideal domain, so all my ideals were generated by a single element R. So we can use Bayer's criterion and deduce that if M is divisible, then M is injective. So for principal ideal domains, the notion of injective is very simple to check. Well, no, it's not very simple to check, but it's something that looks like this. It's a divisible module is injective. In particular for abelian groups, we get some examples. So examples of abelian groups, which is a principal ideal domain, this is Z modules. Then, and this is what I've used already. This guy is injective. Now, of course, if you have, let's suppose that you had enough injectives. We're going to prove this in a second. But let's suppose that you have an abelian group, M. And let's suppose that you can put it inside of an injective, like this Q. Take the quotient. Now, this guy is divisible. Indeed, any guy here and any element on your ring, any integer number, you just lift it to I. This is injective, therefore this guy is divisible. Okay, let's prove that. So pick an element k here. This is surjective by definition. And let's pick an element n here. Then there's an element k bar here such that pi of k bar is this k. And since I is divisible, this k bar is equal to n times k bar prime. And therefore, this k is equal to n times pi of k bar prime. So this guy is divisible. Therefore, this guy is injective. So if we have enough injectives in this category, it's very simple to construct an injective resolution of that M. So we just constructed it. So it doesn't need to be so involved as like taking. So what we did for projectives is we did it by induction, and we constructed this quotient, and then we constructed an injective. We proved, well, this might not be injective. So then we embed the co-kernel of this map into an injective object and so forth, and we continue by induction. But for this category, it's very simple to get a resolution, and we immediately see that actually any object has a resolution with at most 2 elements. So there's not going to be homological constructions on abelian groups that have more than just 2 degrees. Okay, so having said so, if Q is injective, therefore Q mod Z is injective. Just take the embedding of Z inside of Q. So this is injective as a Z module. And we have a resolution of Z, which is useful. So this is an injective resolution of the abelian group Z. What are other examples of injectives? So let's prove it here. So let's take P a prime integer, and let's look at Z adjoint 1 over P divided by Z. So I claim that this is also injective. Okay, so that's the localization at P. So I add inverses for P, and then I divide by integer numbers. So I claim that this is injective. So I want to prove that that is divisible. Okay? So I need to prove that that guy is divisible as an abelian group. And of course, this is the same thing. I mean, for every element of this form, right? What is that? Well, I have this sequence. Z in Z adjoint 1 over P into this guy. Let's put a name. I think the book uses something like this. So that's this. So every element here can be expressed as an element, as an image of an element here, so modulo being an integer. Now you can just clear denominators in such a thing so that every element here can be written as something of the form A divided by P to the K, where K is bigger or equal than 1, and A is co-prime with P. And now these guys are rational. So this set of rational numbers of this form is the same as this guy here. Yeah, that wasn't a question. Okay. Okay. So I want to prove that every element of this form, so grab an element of that form, grab an n, which is an integer number, which is non-zero, and I need to prove that this guy here is n times some other element of this form. Okay, so I need to prove something of the form P divided by B divided by P to some other power k, j, such that n times b divided by p to the j is equal to this a divided by p to the k. So if I prove that that b and j exist, then I'm good, because that will prove that that guy is divisible and therefore it's injective. Okay, so how do we do this? Well, let's clear out p's from this n, because those we can always deal by. So if n was p, then this is very simple to construct. You just multiply and divide by p that we're allowed to do in this ring or in this module. So let's write our n to be of the form n prime times p to some other power, p, j. Did I use I? No. P to the I. Okay? And now n prime is not divisible by p. Okay, so right. So what I would want to do is to find an element such that n prime times p gives me this. And then I can just multiply and divide by p to the I to get this construction. Okay? So if I find a solution to this equation, then I can just multiply by p to the I here and divide by p to the I here, and I get this the same way. Okay, yeah. But the whole point now is that this p is not, p does not divide n prime. So n prime is co-prime with p. So that means that n prime is a unit in, n prime is a unit in z mod pz. And it's actually a unit in z mod p to whatever power, I, j, k, l, for every l. So that means that that guy is invertible. So I can find some b such that n prime times b is equal to 1. So let's use b prime. So there exists some b prime such that n prime times p prime is equal to 1 mod p, or p to the n, for an arbitrary l. In particular, I can do this for p to the k, which is what I want. Okay, okay, so now b is just going to be a times that. For l is equal to k. So if you take, therefore, n prime times b prime times a is congruent to a modulo p to the l, which is p to the k, which is what I want. So that's more or less the statement that these guys are injective. And so that gave us a bunch of injective abelian groups. These are all. Essentially every injective abelian group is a product of elements of this form. And so perhaps I should say that too. So product of injectives is injectives. This is trivial. The fact that product of injective is just abstract nonsense, because it's about like getting an object with maps into it. And products are easy to construct maps into products. So product of injectives is injective. What is not so trivial is to see that these are all, that injective abelian groups are all product of this form. We don't need that statement, so I'm not going to prove it. This already gives us a lot of examples of injective abelian groups. And I think it's enough to prove the following lemma. The category of Z modules, namely abelian groups, has enough injectives. So if you give me an abelian group, M, I need to put it inside an injective object, IM, which should be an abelian group, an injective abelian group. Okay, so what I'll do is I'll define this guy to be, well, hom no. So I think I'll do this as Q mod Z, which is abelian, and as many times as hom from M to Q mod Z. So this is injective. It's an abelian group which is injective. And this is a product of injective abelian groups. Therefore, that guy is an abelian group. It's an injective abelian group. I need to give you this map. Okay, so if you give me M here, I need to give you an element here, F. And F is a function from this set to this injective abelian group. Okay? So F is, I need to produce this F, which takes a map, an element in this set, and it gives me an element of this abelian group. So if you give me some phi here, I need to tell you what that Q mod Z is. And I'm going to define that to be phi applied to M, which is in Q mod Z. Okay? So this is a map that sends M to F, and this guy depends on M, of course. So the statement is that M maps to Fm is injective. And it's a morphism of abelian groups. The fact that this is a morphism of abelian groups is obvious. This construction is additive in M. So if I take M plus M prime, here I'm going to have phi of M plus M prime, and phi is a morphism of abelian groups. Therefore, that's phi of M plus phi of M prime. So the fact that this is additive is clear. So this is a morphism of abelian groups. And the fact that this is injective, well, let's suppose that you have something in the kernel. Let's suppose that Fm is equal to 0. So this means that phi of M is equal to 0 for every phi. And this means that hom from M to Q mod Z is 0. And probably last class or the previous one, this implied that M is equal to 0. So for every abelian group, we constructed an injection into an injective object. So that's the category has enough injectives. I mean, it's a huge beast, but it works. Okay, so now I want to prove that using this, I can go to an arbitrary R modules. So how about the category of R modules? Or probably I'll do this for the category of right R modules. Have enough injectives. And we'll do this with a couple of lemmas. So the first thing to notice is, remember, the essentially only adjunction we've seen is that if M is a right R module, and N is a left R module, then we have this guy, which is an abelian group. Now, if you give me an arbitrary abelian group, let's say L is probably bad name. What's the name of an abelian group? A. Say A is an abelian group. It's a Z module. Then what I can do is look at hom of abelian groups from N into A. And this is a right R module. This we've already done, so phi comes here, and R is in the ring. Then phi acted on the right by R, evaluated at N, is equal, or you define it to be phi of R acting on N. Okay? So N here is a left R module. And these two things were adjoint functors. So what we had is a natural map from hom M tensor R N to A to hom M shoot. This is isomorphic to hom M to hom of abelian groups NA. Now this hom is taken into the category of right R modules. This is a right R module, this is a right R module, and this right R module structure was coming from the left R module structure on N. And this morphism here, well, both sides are just abelian groups, so this is in the category of Z modules. So that's the hom tensor adjunction once more. And this is natural in the sense that if you have a map from N to N prime, then you get a map in the corresponding, you get a commutative square. If you have a map from M to M prime or from A to A prime, you get a commutative square. Now here's the key. The key lemma we're going to use is that if I have, so lemma, and remember we were in this situation, so if you have a pair of adjoint functors, C, and here I have D, and here's my functor G. So let's say that F is left adjoint to G. So if F is left adjoint, and again, I never keep forgetting to check whether this is the notation or the other way around for this symbol, but this means F is left adjoint to G. And let's suppose that G is exact. Then F preserves projectives. For every P projective in C. And conversely, if F is exact, then G preserves injectives. For in C, for every I in D, inject. So what we know is that if we have such an adjunction, then this F, which is the left adjoint, is always right exact. So it always preserves surjections. But now I'm saying something stronger. I'm saying that it preserves actually projective objects. So So not only surjections, but it preserves projective objects. But that only happens if this guy is exact. So this guy, which is the right adjoint, we are guaranteed to know that is left exact. We're not guaranteed to know that is right exact. So right exactness of G implies this condition. And left exactness of F implies this condition. And we had a bunch of situations where that happened. So I'm not going to repeat them, but I'm just going to say something that is quite common. One situation that is quite common in geometry is so a couple of situations that are common for where this happens is if you have a closed embedding, for example. If you have a space and you have a closed embedding into a bigger space, and this I is a closed embedding, then you have two adjoint functors to this guy. So then this guy has to the following situation. Then this guy has two adjoint functors. Either on the left or on the right, and it's exact. Another one that works is if you have, say, an injection of groups. So this is an injection of groups. Or an injection of Lie algebras, or an injection of Hopf algebras, an injection of any algebraic object. Then you get a functor from G modules to H modules, which is just forgetting. An injection of rings, same thing, which is just forgetting. So if you have a representation of G, you just forget the action of the whole of G and remember only the action of H. So in other words, if you have a representation of G, this is a map like this of groups, then you just send it to the composition. So that's sort of like a pullback. That looks like this. This functor, which is a forgetful functor, is exact. And it has two adjoints, on the left and on the right. I'm going to call this restriction functor, has two adjoints. I call them induction and co-induction. So from H modules to G modules and co-induction. And remember, this was looking at tensor by something, by the ring of functions on G mod H, or taking at functions into such a thing. So this was the construction of these two functors that I did. One is left adjoint, the other one is right adjoint to this functor. Both of them are adjoint to an exact functor. I mean, the fact that this is exact is obvious. This is the same vector space with a different representation structure. So if you have a short exact sequence, it stays exact in this category. So it's clear, it's obvious that this functor is exact. So it's obvious by that lemma that one of these guys will preserve injective and the other one is going to preserve projectives, because they're going to be adjoint either on the left or on the right to an exact functor. So that gives us a bunch of examples of when you preserve one kind of thing. And the same thing for this. There are two different adjoint functors here. One is the usual push forward of sheaves. The other one is the push forward of compact support of sheaves. One preserves being a vector bundle. The other one does not. Let's prove that lemma. That lemma is trivial, but it has some nice trivial consequences. Okay, so well, let's prove one. It doesn't matter. Just by reverting arrows, you get the other one by noticing that. So the following lemma is obvious. This is just essentially by definition. I is injective in the category A if and only if I is projective in the category where you revert all arrows. The diagram was the same, just reverting arrows. So I need to prove only one of those two things. So the only problem is that I hope I didn't screw up in the order. Like I could have said that f of I is injective in D if I is injective in C. I think I got it right there, so let's check it. So let's take, okay, so what I do want to check, let's take I to be an injective object in the category C. Oops. Let's take I in C to be injective. And again, what does this mean? This means that, well, I want to check that G of I is injective. So what does this mean? This means that if I have an injection A, B, and this now is in the category, oh wait, G of I, right, so I was injective in D. No one is stopping me. G of I is in C. So these two objects are in C. And I have an injection, and I have a map like this. Then I want to prove that this guy exists. So again, this is hom in the category C, A, G of I. And I have hom in the category C, B, G of I. And if I have a map from B to G of I can compose with this injection to get a map from A to G of I. And the statement is that this is a surjective map. So this surjection means that anything here comes from like such a thing by composing with this map. So that's what I want to check, whether or not this guy is surjective. But now G is right adjoint to F. So this is hom in the category D of FA I, and this is hom in the category D FB I. These are naturally isomorphisms. That's the fact that G and F are adjoint. And now I is injective in the category D. So in this category, this is surjective because I is injective. And this diagram commutes. Therefore, this guy is surjective. Okay, so that proves that lemma. Okay, so we have that if we have a pair of adjoint functors, then if one of them is exact, then its adjoint preserves either projectives or injectives. All right, so I'm going to apply that in this situation. These are the functors. I don't want to erase this board. I don't want to remove that one. Well, I just rewrote this one, so I'm going to remove that one. So these are the two functors that I want to use. I want to use these functors that I have from the category of R modules to the category of abelian groups, and I have this adjunction. So let's fix some of them. Which one? So I want to apply the previous lemma, and let's see. Okay. Let's pick an n in the category of R modules. N is, did I screw up these two things? Yeah, and no one stopped me here. This doesn't make any sense, as I wrote it here. N needed to be a left R module so that this guy is a right R module. So here I've used this, probably I said it and I didn't write it, clearly here, n is a left R module. This tensor product doesn't make any sense otherwise. What is written there is correct, and I've already used the left R module structure on n. And this is a right R module because n is a left R module. But the whole point is that I want it to be flat, which is flat as an R module. So flat over R. So in that case, this functor tensoring by n is exact. So that is exact. So if I do this, then its adjoint functor is that what I want? I think that's what I want. So if I do this, then it's so this guy is left adjoint to hom. We're seeing it here to hom and let's be careful here. The adjunction, I don't want to get this adjunction wrong. So that's a functor that I'm applying it to m. So this is this functor. Let me put a name to this functor. Let's put Tn. Tn applied to m, a, which is isomorphic to hom of m. And now I need to apply a functor to a. Let me call that functor hn applied to a. This is my adjunction. This is my functor f, and this is my functor g. And hn is hom n a. Okay, so this guy is now right adjoint to Tn. So if n is flat, implies hn I is injective R module, and this is a right R module for every I injective abelian module, abelian group. Okay. So for an arbitrary flat module, flat R module, left R module, we get injective right R modules by taking homs into an injective abelian group. It doesn't matter which abelian group we take. Okay. That's just because that hom is right adjoint to tensor. In particular, we can take n to be just a projective module. Okay. In particular, I can take n to be projective. And in particular, I can take n to be just the ring. So projective modules are flat, and I can just take n to be the ring. So if I take n to be the ring, that functor Tn was a general functor that went from the category of right R modules to the category of abelian groups. And when n is just r, this sends, in this particular case, it sends m to m tensor over r with r, which is just m as an abelian group. And it's clear that that guy is exact. Okay? Just sends m to itself. When you forget the R module structure, just remember the abelian group structure. And Hn is non-trivial. This guy grabs A. So this goes from abelian groups like this, from abelian groups to mod R. And it sends A to hom of abelian groups R A. That guy is certainly not exact. So this guy is only right adjoint to this exact functor, and this guy, therefore, is left exact. So that's a left exact functor that sends injective to injectives. Okay, so a corollary of this, for an arbitrary ring R, hom of abelian groups R Q mod Z is injective. Okay, so this is an injective R module. It's a right R module. Okay, so now what I want to do is to construct an injection from M into an injective R module on the right. And what I will do is I'm going to take a product of an injective R module. And how many of these guys I'm going to take? I'm going to take a huge number of them. I'm going to take as many as maps from M into this guy. So now this is an R module, this is an R module, and this is in the category of R modules. So this is the definition of this guy. It's clear that it's injective. Again, it's just a product of injective R modules. The only problem is now to prove that this is an injection, that I have a map from M to here that is an injection. And it's the same thing that we did before. So I have a map from M to Fm. An element here, by definition, is a function from this set to this R module. Okay? So this is the function Fm. And this function Fm, evaluated in the homomorphism phi is a guy there. It should give me an element here. And this guy, of course, is going to be phi applied to M, just as we did before. And again, Fm is equal to 0. If and only if phi is 0 on M for every phi. And this is if and only if this hom from M into this guy is equal to 0. And I claim that this is if and only if M is equal to 0. So I'll let you check why that's the same. But it's exactly the same thing that we did for the case R is equal to Z. So that guy is an injection. And this implies that the category of right R modules has enough injectives, and therefore it has injective resolution. So we've proven the following theorem. R mod and mod r. We've proven it for this, but just take r with the opposite multiplication, and it's the same as this, have injective resolutions. And we can just play around with those, and we can just repeat what we did for tor and do this for ext. Okay? So we have now the notion of left-derived functors and right-derived functors for any functors in the I said left before, so any right exact functor on our module or any left exact functor on our module. Okay, so let's say that M is an R module. Then this functor that goes from the category of R modules, oops, to abelian groups. Is left exact. So we define ext. The ext groups are just the right functors of this guy. How do you compute those? By taking an injective resolution. So let's say that n is mod a right R module. We now know that we have an injective resolution. Then ext star of Mn is by definition the homology of the complex obtained as taking hom from M to this injective resolution. So now, here's one difference with tor. Remember, for tor, it didn't matter if I took a projective resolution of one or the other one. So if I wanted to compute, tor Mn for M a right R module or N a left R module, then I could take tor, I could do the homology of a projective resolution of M tensor with N, or I could take the homology of M tensor a projective resolution of N. So I could derive either way of the tensor product. Now here something funky happens, and is that the tensor product is covariant in each one of the arguments. The hom functor is not covariant in M, it's contravariant in M. So if I wanted to do hom on the category of R modules, dot N, then this is not a functor from mod R to abelian groups, but rather is a functor from here up to abelian groups. So now I need to take an injective resolution. This is still left exact. But that means, therefore, that if I want to compute the derived functors of these guys, then I need to take an injective resolution of this object in this category. And that means the same thing as taking a projective resolution of this guy in the category without taking up. Okay? So if I want to compute ext M N, then I will need to compute the homology of the complex that is obtained by looking at Hom P n in the category of our modules. And the statement is that this is equal to this. This x is equal to that x. So the proof of this is absolutely the same. So we only need to check that the same theorem applies. Okay? So how did we prove this for Tor? What we did for Tor is that we constructed a larger complex that mapped to both complexes computing the left, the right functors. So what we did for Tor here is that we constructed this huge guy, which was taking the projective resolution for M. We tensored that guy over the ring R. We taking the projective resolution for N. This is a double complex. We took the total complex of this. And this guy came with maps to P dot M tensor N, and came with a map to to M tensor P dot N, and that these guys were quasi-isomorphisms. And the trick was to prove that these two maps were quasi-isomorphisms by noticing that this complex was concentrated in this part. So it had exact columns and exact rows, and it was concentrated in one quadrant. Same thing happens for this. If I look at Hom from P dot I dot, this is a double complex. And this double complex maps into Hom P dot N, and maps to Hom I dot, M I dot. And both of them are quasi-isomorphisms. So the proof is exactly the same thing. So the only thing to notice is that this double complex is again concentrated in one quadrant. This only makes sense for positive indexes here and positive indexes here. Okay, so we know now how to compute some X groups, so let's compute some. Yeah. So I've given some examples of resolutions. We have examples of projective resolutions, so I'll try to avoid using sort of like this, because we've already computed this kind of projective resolution for our module. So let's try to use some injective resolutions, and let's see what we can do. So let's look at this situation. Well, before I do that, let's use the projective resolution on one, because this one is interesting, I think. So let's look at the following projective resolution of this ring. Of this Z module. So this is an exact sequence of Z modules, and here is multiplication by P. And these guys are projective. And this is a projective resolution of this Z module. So let's say that I want to compute X groups. And I want to use this as a projective resolution. Then I need to put this guy in the first term. So M is here some abelian. some abelian group. So then this is the same thing as Hom. As the homology of the complex that takes Hom from this guy into my M. So I need to look at Hom from Z into M, Hom from Z into M. Now Hom is contravariant, So, and this map is just the multiplication by p in the sense that this is the same thing as m, and this is m. So we see that x0, as we expect it to be, x0, z mod pz, m. This is the same thing as the kernel of this map, which we defined it to be the p torsion of m. And this, of course, is the same thing as hom. As it had to be, right? Because any morphism like this is defined by the image of the generator of this group into m that needs to be killed by multiplication by p. So we expected x0 to be our functor. We got that. And x1, z mod pz m. Well, this is m divided by p. Notice that this is exactly the rules opposite to what Tor gave us. So Tor 0 gave us the quotient, and Tor 1 gave us the torsion. Okay. All right. Let's look at now what happens if I want to use an injective resolution. So let's look at the following is an injective resolution. But actually, remember that now we could have done this for an arbitrary abelian group. So if you give me an arbitrary abelian group and you put it inside of an injective abelian group, then the quotient is also naturally injective because it's divisible, and you get an injective resolution of length 2 of an arbitrary abelian group. So let's take Homs into that thing. This is for an arbitrary abelian group. And the homology of that complex is going to give us the x groups of A, Z. So this complex here computes the x groups of A with coefficients in Z. I just resolved took an injective resolution of Z. So now what happens if A is torsion? Okay. So again, this thing here, remember that this I defined it to be the Pontryagin dual of A. And if A is torsion, that guy there is 0. So if A is torsion, then I don't have any morphism here. Well, I'll let you study what happens actually when A is torsion. Then you get that this complex here has non-trivial homology at this point. Okay, I have little time. I have 20 minutes. Let's do what's the actual thing that I wanted to do today, which is the following. Let's take an extensions of our modules. No, I don't want to take this one. I want to take an extension of this form, m into e into n. A short exact sequence of R modules of this form is called an extension. Take right R modules, left R modules, it doesn't matter. That's an extension. And I would say that a morphism of extensions is, let me tell you when two extensions are equivalent. I'm going to fix M, I'm going to fix N, and I'm going to declare two extensions to be equivalent if and only if I have a map from E to E prime that makes this diagram commute. Now, exactness of both rows would force this map to be an isomorphism. So I would say that two extensions E and E prime are equivalent if they fit into a diagram like this. Okay. Given N and M and N, you always have one extensions. So you can always take the trivial extension. But there might be extensions E that are not equivalent to that. And that's what we want to analyze. So for example, if the ring R is a field, then there are no extensions that are not of the form. Any extension is of that form. If the ring is interesting from representation theory, then there are extensions that are not of this form. And this is what we want to analyze. Okay? So let's look at this extension, and let's grab an extension like this. Consider an extension E. So I claim that if x1, so claim if x1 nm is 0, then E is trivial. Okay, so what I would want to construct is out of E, I want to construct a class in x1 nm. Okay, so I'm going to be looking at Homs to M. I think I didn't talk about long exact sequences for injective resolutions, but okay, so this should be trivial anyway. So, all right, let's look at this. What do I want to do? How do I want to do this quickly? Okay, so if I have a short exact sequence of modules, A, of objects, doesn't matter, A, B, C, like this, and I take Hom into N, and I apply the functor hom dot m, that functor is contravariant, and I get a long exact sequence that looks like hom cm hom bm hom am x1 I got it wrong. X1 C and so forth. If I apply hom into if I apply hom m n into that sequence, that functor is covariant. I'm getting the arrows wrong. I'm getting the arrows wrong. If I have a map from C into M, I can lift it to a map from B into M by composition. C, B, M, and so forth. But this sequence is exact at this point. That's all I care. The same thing if I do hom, and I'll use both, n dot. Then this guy is covariant, and you're going to get, well, same thing. Now, hom from n into a, you can compose to get a hom oops, sorry, NA. You can compose to get a hom NB. You can compose to get a hom NC, and you get a next one NA, and so forth. And I want to apply this to the sequence ABC being my extension, MEN. So if I apply to A, B, C being my extension, MEN, then what I realize in this sequence here, that this guy is exact at this point. Let's look at what are these terms. I get hom from N into E, hom from N into N, x1 from N into M. Now, I have an element here always, which is the identity homomorphism of N, and this maps here somewhere. So if I call this guy, this is the delta functor. This is an x0 and this is an x1. This is the delta one that we constructed. So delta of the identity is something here. And this is exact. So if this guy is 0, then there exists an element here that maps to the identity. So let me call this guy epsilon of E. Probably epsilon is a bad idea because I think the book uses for a different guy. let me call this actually sigma. So if delta of the identity is 0, by exactness of this sequence, there exists a sigma that is a map from N into E. And moreover, this map here is composition with this. So if I call this guy J, or let me call this guy pi, the map from here to here is that if you give me a map from n into E, you compose it with pi, and you get a map from n into n. So this means that the composition of sigma with pi is the identity of n. So this means that this sigma here is a section of this extension. Okay, so the lemma we just proved is that if delta of the identity of n is 0, then this implies that there exists a sigma, which is a section, from n into E that splits pi. Okay, so now I claim that this implies that that sequence is trivial. So now we have this, we have m into E into n into 0. I'm going to take equal here to n. I'm going to take sigma here into E. Sorry, I'm going to take here m plus n. And what I want to do is I want to give you the map, an isomorphism between these two guys. And this is not a tensor product, this is sum. So the map here sends m n into I of m plus sigma of n. Now, it's clear that this map here is just sends m to m0, and this map here sends mn to n. So now m from here goes to m0, goes to I of m there, m, goes to I of m here, so this diagram commutes here. M plus n goes to n here, which goes to n there, and m plus n goes to I of m plus sigma of n here. And when I apply this, it goes to pi of im, which is 0, because this sequence was exact, plus pi of sigma n, which was n. So this diagram commutes. And now clearly this has to be an isomorphism, because of both of these guys are exact, so the 5 lemma tells me this is an isomorphism, so this sequence was trivial. Okay, so what we know is that if the image of this guy in the x1 group is 0, which happens always that x1 is 0, then any extension of n by m is trivial. So if this group vanishes, every extension is trivial. If this group does not vanish, I claim that this class in x1 depends on E and does not depend on the choices that I made. So that class, which is delta of the identity of n, delta of the identity of n depends on E, on the extension E, and not on the choices that I made. So that's going to be, this is an element in x1 of mn, of nm, that is given by the extension. So what do I mean by it does not depend on choices? Meaning, if I have two equivalent extensions, I'm going to get the same class in x1. So let's prove that, then we'll stop. I think I'm going to have much time. I think I'm going to continue in the next class. So let me tell you what is that we're going to prove. So what I want to prove is that equivalence classes, there's a natural map from equivalence classes. And I've told you what the equivalence relation was. of extensions where I fix the two endpoints. So m and n here are fixed. And I'm allowing e to change. And this is in bijection to x1 and m. The map from here to here, I've already told you one way of getting it. There's a more functorial construction, which is by taking a projective resolution of this n. So if I want to construct this xn, x1 and m, how do I construct that guy? So it's enough to look at this. Oh, m is a bad idea. So let's call the kernel inside of a projective that surjects into n. This you can always do. Just pick any projective that surjects into n and just look at the kernel of that map. So that's an exact sequence like this. And now let's apply hom of that sequence into n. Okay? So let's apply hom of this sequence and that's going to construct you a class here in a very similar way of what we did there. So that's what I'll do next time. I'm going to prove that this does not depend on any choices, and what we gain for free is that this guy is an abelian group. This was a homology. So in particular, this is an abelian group. And if this is a bijection, this means that this guy should be an abelian group. I could just transport. If you give me two classes here, look at the classes in x1, sum them there, and then there should be an equivalence class here that is the sum there, because this is an isomorphism. But that sum is natural here. So this is also naturally an abelian group. And that sum is easy to describe. Just if you give me two extensions, it's easy to construct a third extension. So this is the bar sum. And so I think next class, I was supposed to do this today. But next class, I'll just prove this statement. I'll construct this abelian sum, the bar sum of two extensions. And then I have no clue what I'll do next, because I was supposed to do only this today. All right.